morning to everyone. This class we are going to discuss about a tri-diagonal matrix algorithm. In short, you call it as TDMA. So this lecture topic entirely deals with the derivation of this algorithm in TDMA, and also, if time permits, I'll extend it to solving of 1D problem. So first we'll see what is the importance of this topic, why we have to study this topic. In general, when we consider any flow equation, a flow equation with velocity or temperature, the first step is we are going to discretize the governing equation. Right? Initially we'll have the governing equation. Right? What we'll do with this governing equation, we are going to discretize this. We have many discretization methods, so we'll follow any one of the discretization method. So on discretization, what we get is this governing equation is converted into a linear algebraic equation. So you get a linear algebraic equation, right? So there will be many number of terms in this equation, and we are going to solve for this equation. Right? If it is a temperature distribution equation, that is the governing equation is a temperature distribution based, then when you solve you'll get the temperature values. If it is a velocity based, when you solve you'll get the velocity values, right? So this is what is applicable for any problem in general, okay? Even being a CFD problem or any problem in general, this is how we follow. Now looking at this linear algebraic equation, there are various methods for solving this linear algebraic equation. There are two methods. One is the direct method and other one is the indirect method. You call this indirect method as also iterative methods. Okay, this is the first one, this is the second one. Okay. I can give some examples for this direct method as well as the indirect methods, and I can tell you what are the pros and cons of this method as well as the pros and cons of the second method. When you look at the first method, that is, for example, you can say the Cramer's rule. Okay. The Cramer's rule, and you have the Gauss elimination method. In our advanced mathematics, we would have studied these two methods, right? These fall under the category of direct method. In direct methods, what we see is, when we keep on solving the problem, the computer memory has to store certain coefficients, and those coefficients belong to the order of 2 and 3. That is, say you have a number n, so it is n square and n cube, and you have to store the coefficients of these n square and n cube. You can see the higher order, the powers are of higher orders. So this requires more space in the core memory of a processor, right? That is the characteristic feature of direct method. When you look at the indirect method is, one example I can give is Jacobi and Gauss-Seidel method. Right? So one example of this is indirect method is Jacobi and Gauss-Seidel. In this, you don't have to store the coefficients of very higher orders, rather it would be coefficients of n itself. So this does not occupy much of a computer space. So in terms of computational language, if you say, it is comparatively inexpensive, requires less space, that is less memory, and it is faster also. So that is the reason for preferring to this indirect method, right? But there is also a disadvantage of this indirect method. That disadvantage is, you are not definite about the number of the iterations. Okay, we are not sure, like after how many iterations the problem is going to get concluded. Okay, that is, there is convergence. The solution is going to get converged after how many number of iterations, we do not know. That is a major disadvantage of this indirect. The second one is, we are also not sure whether it is going to converge or not unless really certain required criteria are satisfied. The equation should satisfy certain required criteria, decent criteria. Only then you can say that this indirect method will give you a feasible solution. So the two major drawbacks, we are not sure whether it is going to converge, and we are not going to be sure when it is going to converge. Maybe in the 50th iteration or in the 100th iteration, we are not sure, right? So that is the drawback of this indirect method. Okay. Now, why there are so many methods? Why we'll have to go for this? I'll tell you the reason. When you take any governing equation, first, whether it is a 1D problem, that is one-dimensional problem, or two-dimensional problem, or three-dimensional problem, you don't know about the dimensionalization, right? So the type of dimensionalization that we choose is going to determine the complexity of the linear equations obtained. That is number one. Number two, the number of grids that we are going to take. How many grids are you going to take? How many nodal points that you are going to take? And what are the properties you are going to evaluate? So that is going to make your problem massive, right? And the discretization method that you are going to choose, right? So dimensionalization, number of nodes, and the discretization method. So all these three, in fact, complicate the problem, and we get this type of linear algebraic equation. So we should be wise enough to choose the right method that we want, right? Now coming to the space occupied in the core memory of the processor, we find that indirect method is quite feasible. Yes, it is decent and it's quite good. The other name, again, it's iterative method. But we still have 2-3 drawbacks when we consider this iterative method. And this one I told you, right, Jacobi and the Gauss-Seidel line-by-line method, step-by-step method. This is useful for one-dimensional problem only. And what about the 2D and 3D? Do we really have a solution for it? Yes, we do have, right? So keeping these things in mind, Thomas in 1949, he has framed an algorithm, so that is called as Thomas algorithm. Thomas algorithm, right? Otherwise called as tri-diagonal matrix algorithm. This, in short, we call it as TDMA. Today's lecture is all about this only. The advantage of TDMA is this can be extended to 1D problem. It can be further extended to 2D and 3D by line-by-line method. Right? And it is quite occupying less space, less time. Okay? So what else we need? With no further delay, we'll enter into the explanation of TDMA. Right? So this is the purpose why we are going to study about TDMA. Right? Now I'll teach you the equations and the derivation in this algorithm. Once you understand this, you can manually solve a problem, which I will also do it might be in this lecture or in the next lecture. So you can manually solve, and there are also some subroutines which are available in Fortran, right? Based on this algorithm, you can side by side execute the same problem in that Fortran and also compile your results, right? So we'll move on to that. Step 1. Let me take the system of equations. Okay, let me take the system of equations and make sure that the equations are in the tridiagonal matrix form. I'll also teach you how to write the equations easier to remember. Phi 1 I've taken initially. Phi 1 equals C1, right? And next is going to be D2 Phi 2. You can see that I'm somewhat maintaining this matrix format. Okay, so here it is going to be minus alpha 2 phi 3, and here it is minus beta 2 phi 1. You can see phi 1, they are all in a straight line, whereas phi 1, phi 2, phi 3, phi 4 will come along the diagonal, and on either side of the diagonal you will see one more row of diagonal. For reference, I'll show this, and here also you'll have one more. This is how you have to write. Okay. Now this is your here. This is your C2. This is your second set of equations. So the first set of equation, phi 1 equal to C1, and this is the second step. Now coming to the third step, here I'll have to put T3, phi 3, so on either sides, okay? So this is alpha 3, phi 4, this is beta 3, phi 3, and the constant for this equation is C3, right? Now again I'm going to write the fourth line. So here I'll be getting my phi 4, this is P4 phi 4 minus alpha, and what will be the other side? Here it is minus beta 4 5. Sorry, this is 5. Right? Phi 3, phi 4, phi 2. Likewise, phi 4, phi 5, phi 3. 3, 4, 5, 2, 3, 4. Please don't mess up with the basic governing equations, because with this only we are going to proceed till the end step, right? So make sure that this is written rightly. Now I can generalize this. How will I generalize this? I can write like this. So after so many steps, this is for my nodal 4. So the next one will be 5, 6, like that I can go up to n. Okay? I'm writing it in terms of j. Now, so minus beta j, phi j minus 1 plus dj, phi j minus alpha j, phi j plus 1 equals Cj, right? This is my generalized equation. You can just number the equations. This is equation 1, this is 2, 3, 4, and my generalized equation I've named it as 5. So these are the basic general equations which are derived after discretizing the governing equation, and I've got so many linear equations. Now I have to solve all these linear equations. I am sure that first I'm confirmed that I have 3 diagonals, and now I'm going for the TDMA method, right? Now for the initial part, let us consider the second equation, third equation, and fourth equation alone. Just erase these constants, put it here. I need space over there for further parts. Okay. Now I am considering equation 2 and 3. 2, 3 and 4. For now it is only 2 and 3. Carefully listen, what I am going to do is, I have 2 methods to solve. What are the 2 methods? The first one is forward elimination method. This is the first. And the second one is backward substitution method. These are the 2 methods, right? In TDMA, you have these 2 processes. You have the 2 processes. What is this forward elimination method? I'll tell you. Forward elimination method is nothing but, here you have phi 2, right? Here you have, in this equation again you have phi 2, right? So I can rearrange this equation number 2 and find out what is phi 2. Can I do that? Yes. I'll keep this phi 2 on the left hand side, push all other terms to the right hand side. So phi 2 will have some big value. It might have some 2 or 3 terms, right? That phi 2 I'm going to substitute in this equation, that is equation number 3, and find out what is phi 3, right? So I'm going to substitute this value here. That is, what will be your phi 2? Just for example, I'll write and show. Phi 2 will be, all these terms will go there. That is alpha 3, phi 3 plus beta 2, phi 1 plus C2, and you have this coefficient, right? I'm dividing by this. This is my phi 2 value. You can see this, right? This is my phi 2 value. Now this phi 2 value I'm going to substitute here so that I will eliminate. I will eliminate this phi 2 itself, right? So then I will find out what is phi 3 value. So this is how I am going to do. Next step, what I will do, I will get value for phi 3, right? That phi 3 I will substitute here, and I will find out what is phi 4. So that is how I proceed. So my first step is, I will take phi 2, substitute the value in equation of phi 3, find out phi 3. This value I will substitute in equation 4 and find out phi 4. Like that I will proceed up to phi n minus 1. This is how I will do this. So this process is called as forward elimination process. Right? The second process I tell you, maybe after the completion of the first process I will brief on this. Otherwise I think it will be confusing. Okay? Now we will do with this. I've taken only these two equations for clarification. Now I'm going to start on with the forward elimination process where we are going to take this phi 2 value and substitute in this place. Right? So phi 3 will become alpha 3 by d3 phi 4 plus beta 3 by d3. In the place of phi 2 I will substitute this equation d2 phi 3 plus beta 2 by d2 phi 1 plus c2 by d2. Right? So this has come and the third term will remain the same, c3 by d3. Now what I am going to do is, you can see that d3 is common in the denominator for all the terms in the RHS. I am pushing it off to the LHS. So it will be d3 phi 3 alpha 3 phi 4 plus beta 3 into alpha 2 by d2 phi 3 plus beta 2 by d2 phi 1. All of the terms remain the same. Okay, I am not making any modification. Okay, C3. Now, there is one phi 3 term here and another phi 3 term here. So I am just clubbing those two terms. It is going to be d3 phi 3 minus beta 3 alpha 2 by d2 phi 3 equals, this has gone. Okay. Now you will have alpha 3 phi 4 plus beta 3 into whatever is there here, d2 by d2 phi 1 plus c2 by d2 plus c3. Okay. Now take this common outside, that is d3 minus beta 3 into alpha 2 by d2. Here I am not making any changes, just putting a ditto. Okay, till this it is clear, right? Now this phi 3, I want only a value of phi 3 no, so that I can substitute here. That is, I can get the value of phi 3. I have substituted phi 2 here. I want what is phi 3. That's what I need. Okay. So the next step, I'll erase these two equations around. Let this be here. So phi 3 equals alpha 3. This whole term will come here and divide, right? Divided by d3 minus beta 3 alpha 2 d2 into phi 4, right? Plus beta 3 into beta 2 by d2 phi 1 plus c2 by d2. Okay. Of course, you have c3 here. The whole divided by the same denominator, that is d3 minus beta 3 alpha 2 by d2. And just pausing here, have a look at this. Right? Now this equation, for further simplification, I am making slight changes. Okay, what are those changes? I will tell you. Now you can see this alpha 2 by d2, right? I just call it as A2. Okay, and I have two terms here, no? I call it as C2 dash. Okay, so it will be phi 3 equals alpha 3 phi 4 by d3 minus beta 3 A2. That's all I've done. I'll put this separately here. Let this be a coefficient for phi 4. Okay. This is going to be your C2 dash plus C3 divided by D3 minus beta 3, and let this be, again here you have this term, right? I'll call it as A2. I have simplified this one, I've given a different naming. This one I've given a different naming. Now, this entire coefficient, let me call it as A3. This is A3, 5 plus this, I'll call it as C3 dash. Already we have given C2 dash, no? So this is my C3 dash. Now, is not the phi 3 equation quite simpler than what we had in equation number 3? It's simple, right? Now this I can write from this I can write the generalized form. So phi j equals aj into phi j plus 1 plus cj dash. This is the generalized equation. But I should mention what is aj and cj dash, right? So aj is this. Is going to be alpha j, tj, beta j, aj minus 1. Okay. And what is the cj dash? It is beta j, cj minus 1 dash plus cj by bj minus beta j, aj minus 1. There are so many dj's and bj's, sorry I can't help it, but this is how it goes. Okay, so this is the generalized form. So phi j is aj into phi j plus 1 plus cj dash, provided you know the values of what is this aj and what is this cj dash, right? Please put it in blocks. So this will be your base with which you can further move on to the backward substitution method, right? Now look at this. In the backward substitution method, what we are going to do is, first we'll assume that we know the values of the boundaries. Okay, values of the boundaries meaning A1, An plus 1. Likewise C1, Cn plus 1. Okay, now this is 0, this is 0. So this is equal to n and this is equal to n plus 1. Sorry, I missed the phi here. So it's phi n and phi n plus 1. So these are the boundary values. Now under the backward substitution method, what we are going to do is, this is phi 1, this is phi n plus 1. We first make the assumption that we know the values of the boundaries. We know, right? So phi n is actually c1 dash, which you already have the formula, you can substitute. And phi n plus 1 is again c dash cn1, the same formula, you can substitute. So you will know the parameter values at the boundaries. Now from this I am going to proceed in the upward direction. How will I proceed? From this I can find out phi n, right? Keeping this as a reference. Then again I find out phi n minus 1. Then I find out phi n minus 2. Like this I go maybe 5th node, 4th node, 3rd node, 2nd node, like that I go. So this is called as the backward substitution method, right? So I'm summarizing everything from first. This TDMA is actually an indirect method, also called as iterative method. It can be used for 1D. It can be extended to 2D and 3D. I will show it in the next lecture. I'm stopping with this. Okay. So first you will take the 3-dimensional equations, discretized linear equation you will take, and then you will follow the forward elimination method. For forward elimination method, first you will take the value of phi 2, put it in phi 3 equation, and you get a generalized equation for phi 3 like this. In the phi 3 you have got two constants, one is that is aj and cj dash. You have to take the expressions for aj and cj dash, keep it preserved. This is your forward process. Coming to the backward substitution method, you first assume that you have the values for the boundary values, that is at the boundaries you know the values. So your a1 equal to 0, an plus 1 equal to 0, where you have the c1 dash as phi n and cn plus 1 dash as phi n plus 1. So first step is to find out this phi n. You are moving in reverse direction, you know this. From here you are moving to this. From here, you're moving to this. From here, you're moving to this. Select ways forward. This is the backward substitution method, right? Okay. Extension of this to for 2D, I'll be covering in the next lecture. Say this is your P, this is your north, south, this is your east and west. So line by line. First at this line you'll be calculating, then at this line, then at this line. This is called as a sweep direction. Or if you're moving from west to east, first you'll calculate in this line. Keeping this as reference, you'll calculate the flux properties at this. And keeping this as reference, you'll calculate the flux property at this. So this is called as TDMA line by line method. So TDMA is the same. What we saw here is the same. Either it's a 1D or 2D or 3D. But if you're going to extend this 1D to 2D and 3D, then you use the line method. I'll cover that in the next lecture. So any doubts, kindly mail me. I can clarify. I'm happy to clarify. And I hope this is understandable.